Master theorem. The master method is a formula for solving recurrence relations. An asymptotically positive function means that for a sufficiently large value of n, we have function f of n is greater than 0. The master theorem is used in calculating the time complexity of recurrence relations, divide and conquer algorithms in a simple and quick way. If a is greater than or equals to 1, and b is greater than 1 are constants and function f of n is an asymptotically positive function, then the time complexity of a recursive relation is given by this formula. Each of the above conditions can be interpreted as this. If the cost of solving the subproblems at each level increases by a certain factor, the value of function f of n will become polynomially smaller than n multiplied by logarithm base b of a. Thus, the time complexity is oppressed by the cost of the last level. If the cost of solving the subproblem at each level is nearly equal, then the value of function f of n will be n multiplied by logarithm base b of a. Thus, the time complexity will be function f of n times the total number of levels. If the cost of solving the subproblems at each level decreases by a certain factor, the value of function f of n will become polynomially larger than n multiplied by logarithm base b of a. Thus, the time complexity is oppressed by the cost of function f of n. Solved example of master theorem. The provided recurrence relation is expressed as follows. The time function t of n is equal to 3 times t of n divided by 2 plus n squared. In this context, the parameters are identified as follows. The constant a is 3. The ratio n divided by b is n divided by 2. The function f of n is n squared. Moving forward, the logarithm base b of a is calculated. The logarithm base 2 of 3 is approximately 1.58, which is less than 2. Given that logarithm base b of a is less than 2, case 3 of the master theorem is applicable. This case stipulates that if f of n is a polynomial and logarithm base b of a less than c for some constant c, then the solution is t of n equals to theta of n raised to the power of logarithm base b of a. Consequently, in this specific instance, t of n equals to theta of n squared since f of n equal to n squared, aligning with the n raised to the power of logarithm base b of a term. In summary, the time complexity of the provided recurrence relation is denoted as theta of n squared. Master theorem limitations. The master theorem cannot be used if function t of n is not monotone. Function f of n is not a polynomial. A is not a constant. A is less than 1.